What's up, everybody? Great to have y'all back for the 2024 FRQ number 2. So we're still in the calculator section, right? We're still dealing with that. So I got my calculator right here, and we're going to work through this second question together. So let's dig into it. So number 2, it says a particle moves along the x-axis so that its velocity at time t is greater than or equal to 0 is given by v of t equals the ln of t squared minus 4t plus 5 minus 0.2t. Quite a mouthful, but let's get into part A, first part of this question. It says there's one time t equals tr in the interval 0 to 2 where the particle is at rest. So there's one t tr from 0 to 2 where the particle is at rest. It asks us to find t of r. It also asks us for the interval from 0 to t of r, is the particle moving to the right or to the left? And give a reason for your answer. Okay, so we have this velocity function that's quite a bit ugly. So we're lucky that we have our nice calculator. But let me finish writing it out. We have this velocity. The first question is find where it is at rest. For a particle to be at rest, it means that our velocity has to equal 0. So a great way to find this is by graphing this function on our calculator. So I'll put in the ln. I'll use the variable x instead of t. Our values still all work out the same if we use a different variable all the way through. And minus 0.2x. I can graph it. My window is all messed up, right? So I'm going to make my window from 0 to 2 for my x values, right? Because that's where my t is between. So now I'll click graph. My function's still a little bit off, so I'll use this awesome thing, zoom fit. Zoom and then the number 0. And we see this, right? This curve gives us our velocity over these times. And we see it crosses the x-axis at that point right there. So one of the awesome functions that we have with the calculator is by clicking second trace, which gives us calc. And we have all of these different values that we can solve for. I want to solve for a 0, right? Because I'm trying to guess this value. So I'll give it a left bound, like over here, and a right bound right there. It asks guess. I click enter again, and it tells me that my time, or my velocity is 0, is 1.426, which is perfect, right? This is the time where our particle is not moving, right? So the second part asks us from 0 to t of r, this 1.426, is the particle moving to the left or moving to the right? Well, we look like everything to the left of this on that interval 0 to tr, all of our velocities are positive. So because we have a positive velocity, our particle is moving to the left. Or I'm sorry, not the left, to the right. That's my bad. Positive velocity, we move in the right direction. Negative velocity, we move to the left. So the particle is moving to the right because our velocity is greater than 0. So perfect. We got part A out of the way. Really no calculus for us. We're just plugging stuff into a calculator, which is great. It keeps it super easy for us. But let's move on to part B. Today, just kind of as a moment in time, is the day after Selection Sunday. So the Gators made the bracket, number 1 seed. I mean, we're looking like the most complete team in the tournament. You cannot tell me otherwise. I feel like guaranteed Final Four. if we are national champions, I mean, it would be awesome. Let's look back at the AP test, right, as we're doing our final minute reviews for the AP. Fingers crossed, Florida Gators national champions 2025. We're hoping for the best. But for now, we're going to keep doing more calculus as we wait. But part B, it says find the acceleration of the particle at t equals 1.5. So we're looking for our acceleration at 1.5, right? It says show the setup for your calculations. Is the speed of the particle increasing or decreasing at time t equals 1.5? Okay, so I'm actually going to use this same graph that I already had pulled up. And here's the reason why. This graph is a graph of the velocity. Acceleration, so this a of 1.5, that is the derivative of velocity at a point. So I can use this function by doing second calc and going down to the derivative. And I can type in 1.5, and that will give me the derivative at this point, t equals 1.5. So if I click enter, I get that my derivative, or a of 1.5, is equal to negative 0.999999999, which I'm kind of going to assume is just -1. So my acceleration is equal to -1, which is awesome. That honestly looks pretty simple. So I'm thankful for that. We love to see it. But the second part of the question asks us, is our speed increasing? Is the speed increasing or decreasing? Now we know that speed, I'll write this down, speed increases when, I'll kind of draw these little arrows, when velocity and acceleration are pointed the same direction. It doesn't matter like if they're both pointed positively or both pointed negatively, they just have to both be pointed the same direction. And speed decreases, you can probably guess where this is going, when our particles, velocity and acceleration, are pointed opposite directions. That tells us that our speed is decreasing. So at this point, our acceleration is clearly negative, right? We know it's -1. But what is my velocity at 1.5? Well, the great thing is this calculator that I'm using has a graph of the velocity function. And if I go to second calc once again, I can find the value, which is my velocity function, at 1.5. And I get that it is -0.077, which is a negative value. So because my acceleration and my velocity are both negative, our speed will increase. So that's kind of what we're looking at for this question. So our speed would increase because acceleration and velocity are both negative at this point. Okay, so that is part B. We're doing a solid job. I like these questions because they're kind of asking us like two things at once, right? They're not just asking for the acceleration, but also asking us to like apply it, right? And our understanding of this material is going to be what sets us apart from other people. And those types of questions, big separators, we love those because we're going to get them right. Other people are going to get them wrong, and we're going to do really well on the AP because of it. But let us now move on to part C. I'm kind of just feeling there's probably some displacement coming up because, you know, we've dealt with velocity and we've dealt with acceleration. So now it's time to do some position work. And what do you know? Part C, the position of the particle at time t is x of t. And its position at t equals 1 is x of 1 is equal to -3. So our particle is at -3 when t equals 1. And it says find the position of the particle at time t equals 4, which is basically just asking for x of 4, right? Now, this is actually a very similar question to one that we saw in question 1 of the same FRQ, which is interesting, right? They're very unrelated topics, it seems like, but similar questions. And one thing we learned about position, and this is true for any accumulation function, but our final value will equal our initial value plus the integral of the rate of change over that interval. So this x of 4 will be my position at t equals 1 plus my integral from 1 to 4. Now, I went ahead and wrote v of t, which is my velocity function, right? But this may not feel quite right because, wait, shouldn't this be my rate of change or my derivative of position? Well, the great thing is we know that velocity is the derivative of position. So we get this integral, and we know that x of 4 is equal to negative 3 plus whatever the value of this integral is. And I could do this a couple different ways. Personally, I would go outside of the graph. It's still saved up in y equals, so we're in a good spot. But I would do this integral by doing math, going down to number 9, which is our function integral. We used this exact same thing last time for question 1. So my integral is going from not 0, but 1 to 4. And I'll now type in my long, slightly annoying function, x squared minus 4x plus 5. Perfect. So that is my ln. And then we are subtracting 0.2x. So that's my velocity, dx. Click enter. Takes a little bit of time, but that is the value of this integral, or my accumulation, or in this case, this is displacement, right? We know that the definite integral of velocity over an interval is my displacement over that time. So my displacement is 0.197. If I were to subtract 3, I would get my position at t is equal to 4, which is like negative 2.803, which is a little bit, ugly, but it's okay because, we're using a calculator. Our answers are going to be ugly. But this is a really typical particle motion question where they give us a velocity and an initial condition, and they ask us to find our final position. And our final position is just where we start, which is this x1, plus how much we move, which is displacement, right? So this all works out to give us our final position of negative 2.803. So that is part C. Now, finally, we get to part D. And this question, if we were to ever get it on a non-calculator FRQ, we would be scared for our lives. It's going to wind up super ugly, but we're really lucky. And let's talk about it. So part D says find the total distance traveled by the particle over the interval from 1 to 4. It says show the setups for your calculation. So we know that displacement, we already dealt with it. It was the integral. We'll use these same values, 1 to 4, of my velocity function, dt. This was my displacement, right? But one awesome thing that we learned about particle motion is that if I do that exact same integral, but instead of integrating v of t, which is our velocity, we integrate our speed, which is the absolute value of velocity, we get our distance traveled by the particle. So we can do the exact same integral as before by going to math, going down to function integral, and we can go from 1 to 4. But now when I type in my function, v of t, I can use the absolute value bars, which we can find by clicking math, going over 1, and the ABS, abs, short for absolute value. All the cool kids are saying it. We plug in our velocity function, which is that whole ln of x squared minus 4x plus 5 minus 0.2x. So that's our absolute value. We put dx, click enter. Let's see if we'll get a value. It's buffering. Calculators really don't like absolute value bars, but we finally get it. Tells us the distance is 0.958. And that is the total distance traveled by this particle over the time interval. So, works out really, really easy for us. It's honestly not a challenging question, as long as we remember where the absolute value bar is and that the integral of the absolute value of velocity is distance. Now, I've given these questions in class before, and without fail, people will be asked for total distance and either give this displacement integral, like we solved for in part C, or what they'll try and do is they'll integrate the absolute value, or they'll take the absolute value of the integral of velocity, like this. And this is just the absolute value of displacement, which is not distance traveled. So we need to be really careful. I like thinking about distance as the integral of speed, because if I think about this as speed, I won't forget where the absolute value bars are. But whatever works best for you guys is absolutely fine with me. But that is the answer to part D, and we're done. Calling it wraps on number 2, finishing up our calculator section, getting ready to move on to number 3 with no calculator. But that's all we got. Hope you guys have a fantastic day and happy practicing.